Hello ladies and gentlemen, YouTubers, OpenFoamers. Welcome back to our heat transfer series on OpenFoam. So today we want to talk about conjugate heat transfer. So we have basically looked through Laplacian foam, buoyant simple foam, and buoyant pimple foam. And in the last few videos, we have already talked about time varying boundary conditions, especially for temperature and heat flux. So today we want to look a little more at conjugate heat transfer. So that's chtMultiRegionSimpleFoam. So we want to go through some of the tutorial cases, and we can see how the case is structured and see what we can learn from there. So I'm in the chtMultiRegionSimpleFoam folder. I'll go there. And here we have 4 cases. If you're using the OpenFoam V1906 version or V1812, I mean that's the ESI version. So there's this thing called externally coupled heater, heat exchanger, Joule heating solid, and multi-region heater with radiation. So let's see what's inside the external coupled heater. Alright, so here we have a 0.original, we have an all clean file, all run file, and then we have an all run pre file. So this again, we don't have very much clue of what is inside until we look, of course. We have a readme.txt, we have constant system, and this thing called external solver. So let's take a look at the readme.txt first to see what it is about. Okay. So this is this says modification of heat transfer chtMultiRegion foam tutorial that demonstrates the external coupled function object in combination with the external solver script to simulate coupling to an external code. Well, this may be slightly more complicated, because now it not only has chtMultiRegion foam, it's coupling to an external solver, which we probably don't want to take a look at first, because of course we want to start from something simple. So let's take a look at the next case called heat exchanger. Now, okay, we have the 0.original, all clean, all run parallel, all run pre, and constant in system. So let's take a look at the all run file first to see how this case is structured. Alright, so again we have these 2 basic lines here with the pound sign for comments, cd blah blah blah, and then we have these run functions. Then it runs all run pre, then it runs application get application, which is of course in this case chtMultiRegionSimpleFoam. So we have to look in the all run pre file first to see what it's being done there. Okay, so this is slightly more complicated because it talks about mesh generation and separating the region, the mesh into 2 distinct regions. So there are 2 regions over here. One is the air region, and one is this thing called porous region. So both of them use block mesh to kind of generate the thing. So there are several modifiers over here. We can actually run the all run pre to see what the output is like. And the next thing is to run this application. I think it looks like you're running a toposet for the region of air, and it's using the first dictionary, toposet dictionary.1. You can specify which dictionary to use if you have multiple toposet dictionary to use. Okay. Then it runs this thing called create baffles. Again, we can take a look at what that is much later. All right. So it makes this second thing rotor zone. So it creates a run application, toposet again, and then it uses this system toposet dictionary number 2. And then what it does is next is to remove the sets, what do you call it? Polymesh. So definitely there will be a polymesh file created from running all of these, and for some reason it wants to clean this up. Okay, so next thing it runs is parafoam. Parafoam is basically running paraview from the command line. However, it is not normal to run parafoam within Windows subsystem for Linux. So what we usually do is to just run paraview. instead of parafoam. And then we go touch. We want to do touch some region, and then we do air or porous, etc. Then we set the initial fields by restoring zero directory. We know what that does. If you have watched the earlier tutorials, or at least have some basic understanding of OpenFoam. If not, you can look at the intermediate tutorials or the beginner tutorials. You should know this by now. Restore zero directory copies over the zero.original directory and makes it into the zero folder, so that we can start running the simulation. Okay, so that's all we have. Now, yeah, we can take a look at the all clean file. Oopsie. vi all clean. So, okay, so it will run clean case 0, which removes the zero directory, and it cleans the polymesh for air and porous, and then it removes whatever file that ends with this OpenFoam suffix. Okay, so, and then we have this thing called all run parallel as well. If you have run simulations in parallel, this should be quite familiar to you. Again, it does this all run pre, which is not parallel, and then it decomposes the air and porous region into several small sections, smaller sections. Then it runs chtMultiRegionSimpleFoam in parallel. So it says run parallel whatever application, which is chtMultiRegionSimpleFoam. Then it reconstructs the two mesh regions for air and porous. So let's see what's inside the constant. And then we see there are two distinct regions here, which is not what we are normally used to dealing with. We have an air region, we have a porous region, then we have this thing called region properties and G. G, well, we have seen G before. It's just the gravitational value of gravitational acceleration. And in this case, we have 0 Gs because we use 0, 0, 0. The one with these two forward slashes, these are comments. So we'll not deal with that. Okay, so let's look at region properties. So region properties are this. All right, we have air and porous, which basically are under the fluid category. So you treat the air as a fluid, and you treat this region called porous as fluid. So normally chtMultiRegionSimpleFoam, you're able to treat multiple regions. You can have a solid and a liquid in both, or fluid, solid and fluid in both the same simulation. So you have to tell OpenFoam, hey, which region is solid, which region is a fluid. So in this case, both are treated as a fluid. So it will use all the Navier-Stokes equations in order to solve whatever is in there. So let's look at the air. All right, let's start with what we are familiar with, turbulence properties. Turbulence properties, okay, this is a K epsilon model, nothing too new, with a Reynolds average Navier-Stokes. We can look at thermophysical properties, and we can see this is a HE rho thermal, it's air. Then it has some coefficients for this equation of state. You can see in some other video that, in the last videos before, that we can have very simple equation of state, like PV equals nRT, or some more complicated equation of state. And here we have 8 coefficients. Okay, we can investigate how that polynomial actually comes about, because you see, the transport is stated as a polynomial. The thermal is also stated as a polynomial. And this equation of state is, instead of a simple equation of state, you have this Eichel polynomial. All right, so we can be very specific about how we want to define our heat capacity, for example, our density, and of course the mu, which is the viscosity, and kappa, which I think is related to the Prandtl number somehow, but I'm not really sure now, I can't remember. But anyway, let's continue with what we are familiar with, radiation properties. Okay, so in radiation properties, this is very simple. There's no radiation at all whatsoever, so there's nothing really much to see here. Next thing, FV options. Okay, so finite volume options, FV options, I think. So we will have the air region. So this is air to porous, all right, air to porous. So you will have a type called constant heat transfer interpolation method, blah, 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 blah. Okay, so this is something we will kind of want to look at later on. And then we have this thing called porosity blockage. So it's probably fluid flowing through some porous media. So, all right, it uses some Darcy equation. I'm suspecting to calculate some pressure drop, and it will have its own, coordinate system. All right, and actually so far we have not discussed flow through porous media. Okay, but these are some of the options you can include in chtMultiRegion SimpleFoam. Let's take a look at MRF properties. So MRF1, it says cell zone is a rotor, active yes. So again, it looks like there is some rotor that is spinning within this medium. Okay, so that's spinning within the air medium. So that's part one. The air medium is done, and the interface between the air and the porous medium is also being calculated. So we can look at the turbulence properties for the porous region. Okay, it's a laminar simulation here. We can take a look at thermophysical properties. Again, this is water. So it's some kind of water flowing through a porous region. And then we can take a look at FV options. And it says a constant heat transfer, air to porous, okay, etc., etc. So porous to air, this is the heat transfer, how you specify heat transfer here. So it looks like FV options is a pretty important file. So this is all we have for the constant. All right, let's take a look at the other the system files, and we try to run the all run pre in order to see which file does what. Let's go to system, and again we notice that what is slightly different is that we have, for both constant and system, we have an air and we have a porous. All right, so let's look at control dictionary. So this is the usual control dictionary that we are used to, nothing too fancy here. Decompose parallel dictionary. Okay, this is a Scotch method, very simple method. I think in the X direction it divides into 2, the Y direction divides into 2, and we have 1. Okay, 1 in the Z direction. So total number of subdomains should be 4. So it splits the whole case into 4 regions. Okay, FV schemes and FV solutions. All right. Oh, there's nothing here at all in the FV schemes. Okay, that's kind of weird, on first sight at least. And again, FV solutions, there's nothing except this pimple number of outer characters equals 1. So where are all this vital data? Well, we'll have to look in, for example, air, and we'll realize, oh, in air, there's this block mesh dictionary, decompose parallel dictionary, FV solution, toposet, FV schemes, and create baffles dictionary. So you notice that for each region, we need to put the rest of the dictionaries in there, except this control dictionary, and then you have to have some kind of empty files, the FV schemes and FV solutions, along with the decompose parallel dictionary. So let's take a look at the block mesh dict. So it looks like a very complicated block mesh dictionary. So we have some little more complicated geometry with some arcs. And look at the FV solution, and we see all the solvers are over here, the simple solvers, all right, with some relaxation factors. So these are the solver inputs for the air system. So we look at the FV schemes. We take a look, it's a bounded upward Gauss. All right, so there's some correction factor there. Gauss linear limited corrected in the Laplacian schemes. Okay, so it's a steady state simulation, which is correct for SimpleFoam. Okay, I mean chtMultiRegionSimpleFoam, yep. So let's look at the create baffle.dict, create baffles dictionary. Okay, so again, it looks like there are some patches. Okay, there are some patches that are created so that we can have some sort of a rotor blade spinning in this system. So okay, we will want to look at what create baffles actually does. This is something new to learn. And let's take a look at porous. I hope I didn't miss any other thing there. Porous, clear. We see a block mesh dict. Okay, we see a block mesh dict there. No issue. Nothing new there. Decompose parallel dictionary. Again, the parallel dictionary is exactly the same. FV schemes. Okay, we see all the necessary input files. And we look at FV solutions. And we see another set of input files for this. So what can we learn from here? At least by examining the structure. It looks like we need to create the input files into specific categories based on your region. Let's say you want a fluid region, you have to create a fluid category, for example air, with all the necessary components in it. So you have to specify the thermophysical properties in the constant. You have to specify the FV schemes and FV solutions in here, along with the block mesh and everything. Okay, so for the other region, in this case the porous, you have to separate it out, and we suspect that it's a similar thing here as well. So you see, air and porous have different zero files. So again, in the air file we have T, U, alpha T, epsilon K, new turbulent, and P RGH. Same thing for porous. Okay, so for porous we have something a little more complicated because I think it's a different solver. Again, we have not looked through porous regions yet, so that may require us to take a look at what the porous region actually, how do we solve porous region cases. That's another video for another time. Okay, but this is basically to see how this case is structured. Okay, so if you take a look at maybe this thing called Joule heating solid, maybe this is easier for us. Alright, since this is the third tutorial case, so I look through two as well. So let's take a look at zero.original. We see one solid in here. So there's only one region called the solid region. So we have a T and P and a Joule heating source. So let's take a look at Joule heating source, the V file. Okay, so this is this looks like alright, a left and right, top and bottom are zero gradient, and these two things have a fixed value. Great. Okay, so that's the Joule heating source based on, maybe it's a voltage, maybe the V stands for voltage, but let's take a look. Alright, and now of course we want to take a look at all run, which says here all run pre, run application, and create graphs. So this is solid with some internal heat generation. Alright, so for that we have a run application -s solid block mesh region solid, and the paraform here to do post processing and then restore zero directory. Okay, all run. Okay, and let's look at create graphs. Okay, so this is looks like a script to create some graphs. Okay, but we may or may not want to actually activate that script because it's kind of out of the scope of our learning for now. It may be useful, but may not be needed. So let's take a look. Region properties, we need to specify within again chtMultiRegionSimpleFoam solid. We only have thermophysical properties, so this is essentially solving it like Laplacian form. So let's take a look at system, and we'll see control dict. decompose parallel dictionary, FV solution, and solid. So control dictionary, we leave it here. We look at decompose parallel dictionary, 4 domains, method is Scotch, FV solution, nothing there. So again, when you're in the main directory, the only thing you really need to change is this control dictionary file. These two, I mean FV solution is kind of a blank file, and decompose parallel dictionary, yeah, we have something for the parallel running of parallel system, running of parallel, what do you got it? Yeah, running parallel simulation. So again, here we have block mesh dict, FV schemes, FV solutions, and FV options as usual. So FV options is this. We have a Joule heating source. So if you want to activate Joule heating, heat generation, we can use this. And basically you can put the Joule heating coefficients, and you can specify anisotropic electrical conductivity, or you can specify the sigma, which I think is some conductivity as a function of temperature. Okay, so it looks like a some form of a graph where you linearly interpolate those. Okay, FV schemes. Okay, we have DDT, gradient Laplacian schemes, and all of that. It looks like most of it will be using Laplacian foam. Okay, and we look at FV solution. Okay, so we have these solvers for H and Joule heating source V, and then the SimpleFoam is here, relaxation factor is here. These are the inputs to the solver file. And we have also the block mesh dictionary, which is again a very simple kind of a thing. Yeah, it's basically one block. All right. Okay. So this Joule heating part, it looks pretty simple. The case is pretty simple. There's only one region, and yeah, there's only one region, and yeah, there's no fluid and solid interacting. So let's take a look at the last one, multi-heater with radiation. Okay, let's see the constant. We have a bottom air heater, left solid, right solid, top air. Okay, I realize I'm running a little over time. Don't want to make this video too long. So yeah, basically we have run through 3 of these tutorial cases. They look pretty complicated. This one seems to have some porous media. This one seems to have an external solver coupled to it. This one, Joule heating solid, it basically only has one region. All right, and probably what we want to look at next is this tutorial file, which we might, we want to look at it in the next video. Again, to study how these cases are structured, so that we can construct our own place eventually, or tweak the cases. So thanks for watching. I'll see you guys next time. Bye bye.